All right, here we go. This is the first lesson of the last unit of calculus and vectors. And it's really interesting because we're going to see how this goes full circle with a bunch of stuff that we did in grade 9. Now, I've said this kind of thing before, and we've noticed this before. When we do rates of change, we talk about how a lot of that is related to the stuff that you do in grade 9 about rates of change and linear relations and that kind of thing. And it's absolutely true. But this is similar to that, where a lot of what we're going to do over the next couple of days, and we're going to extend it, obviously, we're going to take a very different look at it, but it's going to be very similar and reminiscent of things that we did in grade 9. Really neat as we finish off the course and finish off high school mathematics, that it comes all the way back to the beginning of high school mathematics. So we're going to spend a couple of days on this. A lot of what we're going to do is going to be very similar to grade 9, but we're going to use different notation. And that's really what the first half of this entire unit is all about, is getting used to the notation that's required. And then the second half of the unit, we're going to be actually doing stuff that's very new with that notation, that kind of thing. Okay. And so we're going to spend 2 days on lines, and then we're going to spend a couple of days on notation of other things that we've never seen before we can move on and start doing the other new stuff. Okay. And today we are going to introduce a few types of the notation, not all of them. And this says equations of lines in 2-space and 3-space, although we're actually not really going to talk about 3-space today, but we're going to start the process of notation that's required for it. So I left it in there in the title of the lesson. And you can see some of we're going to see vector and parametric today. We're not actually going to see symmetric today, but that's tomorrow. But those are all different types of notations that we can use to represent the equation of a line. And that's why it's coming all the way back to grade 9, because grade 9 is all about equations of lines. So let's tap into that knowledge. We're going to start with that. This is the stuff that we already know. It's been a long time, so we may not know it. It may not be really fresh in our minds, but this is stuff we learned back in grade 9. Before we even get to this, what were the different ways that we would be able to talk about a line? Well, y equals mx plus b. Okay, that's slope and intercept form, we call that. Okay, so that's a popular one because it's very useful. We have this one that we have already talked about in this course, because we did a lot of equations of tangent lines in the calculus portion, and so that's called standard form. It's actually another one that we at this school at least don't express lines this way. For us, it's actually a formula, and the formula is y minus y1 equals m times x minus x1. And this is point slope. So whereas y equals mx plus b is slope and intercept, this is point slope. And that's a formula for finding equations of a lines. But in fact, some schools or some sections of math would use this as the actual formula. So I might have something like this. And that would be a line that has a slope of -2/3 and goes through the point 5. Hold on, let me write this down. 5, -4, because I would be changing the signs of each of those, right? So this has slope and a point. This one does. So that could actually be another way, but we don't really use it at our school. At any rate, those are sort of the different formulas and general forms of equations of lines that we see in grade 9. And that's the notation that we use. And for all of those, in order to find that equation and state it, now we might have to do a little bit of algebra, like rearranging to put it in the right form, but we always need slope and a point. And then we can determine the equation of a line. And I'm not going to go through that process. So for example, well, I could use these ones, m equals -3/2, and then my point is 5, -4, right? So I can use that as my example. And if I wanted to come up with the uh, slope intercept form, I would have to sub in the slope, sub in the x and y, sub the point in for x and y, solve for b, and restate, right? So I can't write, I'm not saying that I can write the equation directly given slope and a point, but that's the information I am required to have to to eventually be able to write the equation line. Okay, that's all grade 9 stuff. We are going to see some of the standard form is going to be a big one that we're going to see. And, you know, in this course in general, we needed some of this stuff for some of the other things we did. So some of this is useful, but really this is just reminding us of what we already know about lines from grade 9 and you know, all the different properties they have, like lines can be parallel or they can be perpendicular and all that kind of stuff. That's all gonna, like that thinking and those properties are the kind of thing that's gonna be important for us in this unit of this course. But mostly what we're gonna do is working with lines, but working with different notation for those lines, okay? And because what we're doing is vectors, one of the notations that we're going to use is using vectors. How can I represent a line? And for now, we're still working in two space. How can I represent a line using vectors? Okay, so where in grade 9 and previously in Cartesian space, not using vectors, we needed slope and a point. When we're using vectors, we need a point, but the point is useful because it gives us a position vector. So a position vector where the tail is at the origin and the tip is at any point on the line, okay? So that's one thing we need. So similar to having a point, but what we actually want it is as a vector. And then the direction of the line. And that is comes from the direction, or gives us the direction vector. So whereas before we needed slope at a point, now we need a position vector and a direction vector. But if you can understand that the position vector and the direction vector are very similar to the idea of having slope at a point, then I think that would help us understand what we're doing and where this is going, that sort of thing, okay? So that's what we need in order to find the equation of a line. And you know, part of what we're going to be doing is finding equations of lines or using equations of lines, understanding equations of lines. So we have to know how you can write it. We have to know if you have it, how you can use it. Like those are the kinds of things we need to know. And that's what we're going to work on over the next several days, the first half of this unit. It really is about getting used to the notation and being asked to do all kinds of different things to get us used to the notation and how to work with these things. Just like in the last unit on vectors, where we were learning about just the idea of what a vector is and working with this notations. And we were always, remember, asked to do all kinds of different little things. Find a vector orthogonal to. Find a unit vector in the opposite direction of. All those different little questions that we were asked to do are just getting us working with the notation and doing this stuff. So the next few days are very similar to that, I would say. Familiar with the notation. Okay, so let's take a look at this example. Consider the line y equals 1/2 x plus 4. So this has a slope of 1/2 and a y-intercept, which we often refer to as b of 4. Okay, so I'm going to graph this, and my y-intercept is 4. And how do I use my slope? Well, slope is rise over run. So if the slope is 1/2, every time I go up 1, I go over 2, and that gives me another point. And then I go up 1 again, and I go over 2, and that gives me another point. So rise and run, up 1, over 2, and from here I can go same direction. In this case, I'm going to go down 1 and go the other way, 2, down 1, the other way, 2, and I'm going to get rid of these lines. And I notice that now I have a bunch of points that I can line up and draw, hopefully, a nice line, maybe like that. I think it was better like this. Okay. Oops, too far. I'll get it right. There we go. Okay, there's our line. Okay, that is the line y equals 1/2 x plus 4. Okay, um, now we're going to turn this into a vector form of an equation. Okay, and so just looking at this line, I could pick any point. There's nothing magic about the point that I'm going to pick, but I'm just going to go ahead and pick one. So a point on the line, P naught, could be 2 comma 5. Okay, so that's this point here. That's the one that I chose, but I could, in this case, I could have chosen any of them. We got to dive into this notation somehow. So we're just going to pick a point and go. Okay, now this gives us the position vector we'll call it vector P, and we're going to write it as a vector with square brackets, okay? And that is vector 2 comma 5. Now, now remember, it's going to be important. Vectors do not exist in a particular position. But what that vector notation means is if I set the tail at the origin, then the tip will be at 2, 5. So that is vector P. Okay? And again, it could have been any point. So go with me on this. Let me get this finished. That maybe doesn't make any sense where I'm going with this, but trust me, I'm going somewhere with it. Now, for the direction vector of the line, and we're talking about this line, okay, we need a vector with its tail on the origin, but one that is parallel to the line. So what would that direction vector be? And so again, we would have infinite possibilities here because it could go either direction and the length of it doesn't matter, but I'm going to make it simple and keep the length sort of minimal. And you know, your direction maybe will have something to do with how many negative signs you want to have in it, that kind of thing. But generally speaking, we're not looking at lines and picking these things. That's not what we're going to end up doing. We're just introducing the notation right now. So how would I be parallel? Well, parallel has to do with slope, and the slope of this is up 1 over 2. So from the origin, I am going to go up 1 over 2, and I'm going to put the tip there, and the tail, again, has to be at the origin. Okay? So that is going to be the direction vector, and I'm going to call it D. And so D, a vector D, is 2 comma 1. So I got to get the x and the y in the right order there, obviously in the right places. So 2, 1. It's a vector with its tail at the origin and its tip at point 2, 1. Right? So that's my direction vector. And if you think about it, this direction vector is going, let's see, up 1 over 2. Okay, just like this is going up 1 over 2 as well. Okay, so if we think about what we know about slopes and parallel slopes from grade 9, we can see that those are parallel, and we designed this vector with the slope of this line in mind, so they are definitely parallel. And that means, here comes the notation, the equation of this line in vector form is, so we write it like this, x comma y equals, we start with the position vector, and then t times the direction vector. So this is my position vector, and this is my direction vector. And it doesn't have to be t. We use different variables at different times. So we often use T, S, R, those ones, okay? But T is a common one, but that's just kind of a random uh, variable, okay, that we're using. And that's just part of the notation. It's got to be there. You'll see why eventually. So that's what the vector equation of a line looks like. I mean, this is just notation. It doesn't make a lot of sense to us yet. I am going to talk about why it works and why it makes sense. But just generally speaking, that is the notation, and notation is what it is, right? So that's just how we write it. And so you got to get used to it, and you got to understand that the position vector refers to a point on the line, and the direction vector is kind of like the slope of the line. Why does this work? And why could I choose any position vector? So the way that this works and the way that this defines a line is T is called a parameter. And what that means is I can choose any value and set T equal to that value. So up here, if I have an equation of a line like y equals mx plus b, I would be choosing values for x and then calculating values for y. That's how that would work. If I needed to generate values on that line, that's how I would do it. Vector equations are a bit different, okay? I just choose a value for the parameter t, and that will allow me to generate points on the line or position vectors, 2 points on the line or whatever, but it would allow me to generate points on the line, let's say that. So what if I said t equals 1? Well, then I would take, so if t equals 1, now I'm just talking here. I want to explain why this, what the point of the vector form is, okay? If t equals 1, then xy, whoops, will equal 2, 5 plus 1 times 2, 1, which will be 2 plus 2, which is 4, 5 plus 1, which is 6. And 4, 6 is a position vector to a point on the line. Now this is a vector, but that means 4, 6 is a point on the line. And what if I chose 2 as my value for t? Well, then I'm starting, see what I did was I started at this point because that was the position vector that I used, 2, 5. And I went the direction vector once because I chose 1 to be t. So I went up 1 and over 2. What if I said t was 2? Then I'd be starting at this point and I'd be doing that twice and I would end up at that point. And what if I said it was -1? Well, then I would start here and I would go back that direction to that point. And so you can see that I can pick values for t and sub in for them, and all the different values of t for every real number, right, will take me to all the different points on that line. Okay. Let me get rid of this junk because it's kind of messing stuff up. Whoops, too much. And just make sure that we all have understood what I'm talking about there. And just explaining why this works. It's that parameter t that's doing the magic. I'm subbing in for it. And that takes me different multiples of this, which you can see is kind of like my slope. Because every time I change t, I'm changing both of these values, right? I'm multiplying, I'm scaling both of those values up. T is a scalar, the others are vectors. And I hope that makes sense, okay? Because that's going to be important. And that's why, now I want to go all the way back because I didn't really mention this because I think it would have been confusing at the time, but now it might make sense. That's why a point on the line is 2, 5, but what I need is the position vector. Because otherwise, I would have been adding a point to a vector, and that doesn't make sense. You can't add a point in a vector. I can multiply a vector by a scalar, okay? And I can add 2 vectors together, but I can't add a point in a vector. So this has to be a vector for the math to make sense. T is a scalar, and it's our parameter. And the direction vector is going to be parallel, so that no matter which point I start at, I will be going some multiple of t up and over and always landing back on the line. And again, that's why any position vector or any point on the line will do. I started at 2, -5, so I can start here and go wherever I want, or I could have started here and gone the other way, and I still would have gotten sort of everywhere that I need to get to, okay? And so that is vector equation of a line, vector form of the equation of a line. And I hope that makes sense. I hope we understand why. We're going to be using it a lot, so it is important that we understand it. This is just a restatement of what I've already been talking about. Okay, x naught, y naught is a position vector to any known point on the line. Now we see why that's important. M1, M2, or D1, D2 if you prefer, because we're talking D, the direction vector, but obviously the variable you use there doesn't matter, is a direction vector that's parallel to the line. T is an element of the real numbers, okay, so that's important, and it's any, so it can be decimals, fractions, obviously, integers, positives, negatives, irrational numbers, everything works, okay? And then X, Y, which is the result of adding the two, is the position vector to any point on the line, right? And by changing t, I will get any and all of the points on the line, or position vectors to those points, okay? So this is vector form of an equation of a line. It is one of the many forms that we're going to talk about, and it's important, okay? Some of them are going to be a little bit more important than others. This one's fairly important. Okay, and some of what we do over the next several days, as I've already said, is just doing things to get used to the idea, like, of working with this stuff, okay? So one of the things maybe we want to know how to do is if I have 2 points, and I'm going to go ahead and graph these 2 points. So let's see, I've got 3 and -2, so that's point P, and I've got -1 and 5, and so that's going to be point Q. I'll do it up here, okay? And how do I write the vector equation for the line through P and Q, okay? So not only is this going to get us thinking a little bit and doing some, using some of the skills we already have, but it's going to get us used to working with vectors and the equation of a line and that kind of thing, right? Used to this notation. Now, let me go back up. What do we need to come up with a vector equation? We need a position vector, which is a vector to any point on the line with its tail at the origin and its tip at any point on the line. Well, we've got 2 points, so we can just pick one of them, okay? So if I'm going to pick P, because why not? And P, vector P will be the vector 3, -2, okay? And that goes with point P, 3, -2. But I need it to be a position vector, so I'm just defining it as vector P. And I am going to, first of all, before I go any further, I'm going to draw the line, because I haven't actually done that yet. Okay. And then I'm going to draw in vector P. Okay, there's vector P. Now I need a direction vector. And of course, if I have a graph of the line, I could just kind of eyeball it. I could just count it. I could just figure it out using the graph. But what if I didn't have the graph? What if these weren't friendly enough numbers that I could even graph them if they're decimals or irrational or something, or if they're too big to graph, okay? So we want to be able to do this algebraically by just computing, not by counting squares on a graph. So I would challenge you to think, how can I determine a direction vector, a vector that's parallel to the line? Well, how about either vector PQ, the vector from P to Q, that is parallel to the line, or, of course, vector QP. That would also be parallel to the line. So I could find either of those. So, and I'm going to do PQ because why not? So my direction vector is going to be vector PQ. And remember, this is one of the things in the last unit, in unit 7, I made a big deal that this is one of the skills that you're actually going to be using. It's not just about getting used to the notation. That's one of the ones you're actually using. So here we go. Now we're using it. Okay. And so this was something where you have to remember how to do this. There's a little trick to finding the vector between 2 points. And it is, anybody remember it? Subtract backwards. So vector PQ, actually, let me do this. Let me just do this right here, is going to be equal to OQ, so from the origin to Q, minus OP. Okay, and remember, the order counts. So if I'm doing PQ, then it's Q minus P, and it's actually OQ minus OP. So OQ is the direction vector from the origin to Q, which is -1, 5. And OP is the same as P, which I did before, which is with its tail at the origin to point P. So that's going to be 3, -2, which means I've got -1 minus 3 and 5 minus -2, which is 5 plus 2, which is -4, whoops, and 7. And let's take a look at this thing. -4 and 7, 5, 6, 7. Okay. Is that parallel? It sure is. Whoops, too far again. That looks good right there. Okay. And remember, vectors do not exist in a particular position in space. They exist anywhere. So even though we calculated P to Q like this, I can take that vector and move it over there, and now I've drawn it there. And so this is my direction vector D, which was P to Q. I've just moved it to a different place. Okay, and that means that the equation of the line is my position vector, which I chose vector P, plus my parameter T times my direction vector. And that's how I determined the equation, the vector form or the vector equation of that line between those 2 points. Okay. So again, you're starting to see that even just little things like finding the vector between 2 points, these are things that we can't take for granted anymore. We got to know how to do them. Okay. Here's another one of these questions, just gets us used to doing these kinds of things. And we're going to be doing this kind of thing all the time. Determine if this point, -5, -16, is on the line. Okay. So how are we going to do this? And now this is one of those skills that we haven't got there yet because we've only looked at the vector form. But depending on whether we have different forms of the equation of the line, you might pick a different form for different questions. Okay, but all we have right now is vector form, so we have to use vector form. So here's what I'm going to do. How do I find the x value? Well, the x value will be the x part of the position vector and the x part of the direction vector, right? That's what's going to give me the x value of the resultant vector there. So my x is going to equal 3 minus 4t. Okay, so that's minus 4 times t. That's where I got that from, starting at the position vector 3. Whereas y will equal negative 2 plus 7t. Okay, so that came from the y portions from my equation there. And so what I'm going to do is I'm going to sub these values in and solve for t. Okay, and again, go with me. This is the first time we're seeing this. So you're going to have to go with me. So subtracting 3 from both sides, dividing by negative 4, and I get t equals 2. Okay, and then again, subbing negative 16 in. And I add 2 to both sides. So I get negative 14. Whoops. And I divide both by 7. And I get negative 2, or I get t equals negative 2. Now, what does this mean? The fact that they're both 2, but one's positive and one's negative is just a fluke. That's irrelevant, by the way. Okay. So what does this mean? The t's are not the same. That means if I put in 2 for t into this equation, I would have got x is negative 5. But I would have to put in negative 2 for t into this equation, and that would to give me the negative 16. So a single t is not going to take me to that point, right? That's what that is saying. So t is inconsistent. Therefore, negative 5, negative 16 is not on the line. Okay, that's what that means. If I got a consistent t, that would mean subbing that value of t in to this equation that I have would take me to this point, right, or to that vector. And so that would mean that the point was on the line. The fact that t is inconsistent means the point is not on the line. Now you can just remember that if the t is inconsistent, the point's not on the line, but I think you want to understand it. I think that's going to be very useful, okay? So think about that a little bit further if it's not quite clicking. I think that the more you can understand about this, the more everything we're going to do down the road is going to make sense. Okay, so what's next? Find another point on the line. So we kind of talked about this before. To do this, you just pick any value for our parameter t and sub in and solve, and that will find a point. So I'm going to pick 2, and let's see what would happen if I do 2. So I choose t equals 2. Now what's interesting is we're going to do a whole bunch of really tricky stuff, and then there's going to be a question on the quiz or a test or something like that that says find a point on the line, and you're going to have vector form, and people won't know how to do it because you know we don't do a lot of this in this unit, but it's a simple idea. You just pick a value for t, sub it in, and calculate, right? But people forget that that's what that means. So try to remember that this is actually how these equations work, and hopefully you'll remember to do that. So this is 3 negative 2 plus t, which is going to be 2. Let me just make sure I'm getting this right. Yep. Negative 4, 7. So when t equals 2, I get 3 negative 2 plus 2 times negative 4, 7. which is going to be 3 minus 8, so -5, which makes sense because that's where the 2 came from above, and then -2 plus 2 times 7, which is 14, so that's going to be 12. So this point, therefore, that's not a point. Now, some people would also leave it at that, but that unfortunately is wrong. You're not going to get full marks for that because that's a vector and it asks for a point on a line. So you've got to say, therefore, -5, 12 is on the line. You have to turn that into a point. Okay, have to. Be very careful about that. And -5, 12, let's see. Oh, just off my graph. That's bad planning. -5, 12 does look like it's going to go through that point. So that does fit with the graph. And it means, what does it mean? Let me go back. It means that if I had asked, is -5, -12 on the line, or sorry, -5, +12 on the line, I would have gotten t equals 2 for both of those, right? I would have subbed in 12 and I would have gotten t equals +2 there as well. And a consistent t means you can do that and it gives you a point on the line. That's what it means. Whereas an inconsistent t wouldn't give you a point on the line. Okay? Okay, so there's a couple of different things that we can do. There's vector form of the equation of a line and a couple of different little things that we can do with vector form of the equation of a line. And that's just in 2-space. Okay, whoops, everything we've done so far is just in 2-space. We are going to extend it to 3-space eventually, but not yet. The second and last for today, but we're going to look at another one tomorrow. The second type of equation of a line that we're going to look at, there's nothing special about it being related to vectors here. This is just another way that we talk about functions and equations of lines and different things like that. And it's kind of a big one. We really just touch on it a little bit, obviously, in this unit of this course. But in certain branches of mathematics, this is everything. You would use this over and over and over and over again, okay? And it's called parametric equation of a line. So this is a pretty big deal, okay? And this one, and of all the different versions that we're going to look at, some are more useful than others. Parametric is one of the ones that is useful. Even for us, we're going to be using parametric a fair bit, okay? They're definitely, this is a functional equation of a line. We'll use the vector form as well. It's the other one that we'll look at tomorrow that we don't use quite as much. All right, so example 2. So this is how does the parametric equation work? Well, look, I've broken it up into its separate parts. So I've broken up the x separate from the y, and I write it with this, and it's kind of reminiscent of piecewise functions, but it's not the same thing as that really. It's breaking it up into its x and y parts separately, and the parameter in this case is t, just like I had a parameter up here. And in fact, when I look at this, right there, those are like the parametric equations. This was just the x component, and this was just the y component that I broke up separately. Same thing is happening here, okay? Okay, and t is my parameter, it's an element of the real numbers. So given the parametric equation of the line, L1, equal, or often we use a colon there, okay? X equals, the x component is equal to -2 plus 3t, and the y component is equal to 4 plus 5t. Write the vector equation of line. So this is another thing that we need to know how to do. So we need to know what vector is, what vector form looks like, and we need to be able to, as quickly as possible, flip back and forth between the different versions. It's fairly easy to go between parametric and vector once you know them both and see the connection, okay? This constant in each gives us the position vector. So, of course, we always start with x and then go to y. And the coefficients of the parameter give me the direction vector. And the parameter is t. I'm not choosing that. That was given because it's t in there. And so 3, 5. So that's a vector form. So you can see that I just pulled it directly out of the numbers in parametric form. And similarly, if I was given vector form, I could easily turn it into parametric form. And this is what I said before. Sometimes parametric form is better to use. Sometimes vector form is better to use. That's part of what we're going to come to terms with for different questions. Which form do I want? And I'll turn it into that form in order to use it. So sometimes you may just have to, for yourself, choose which form to use, okay? Find two other points on the line. So I'm just going to pick random, or not random, but I'm going to make them make sense. But I'm just going to pick values for t and sub in and solve to find the result, okay? So let's say t is -1. And for this one, I'm going to use vector form. And there's no reason why I'm using one form or the other. I'm going to use both forms to get used to all the different forms that we can do. So t is -1, so -1 times 3, 5. Okay, just using vector form there, which equals -2 minus 3 is -5, and 4 minus 5 is -1. So again, therefore, we got to turn this into a point. Have to, really important. -1, -5, -1 is my point. Okay, let's pick another one. Again, I'm going to make it easy. I'm not going to pick pi or something like that. I'm going to pick 10. And I am going to use parametric form. Now, parametric form would be a little bit of a weird form to use because it just doesn't lend itself nicely to this kind of line by line math, but we're going to try it anyway. And we can see that subbing in a parameter, it's the same parameter, right? T, same thing, whether we have vector form or parametric form or whatever. So then this ends up being x equals -2 plus 30, which is 28, and y equals 4 plus 50, which is 54. Therefore, my point is going to be 28, 54. It's just this part here that's awkward, right? Because I've already got equal signs inside. So having equal signs here, and generally we have it like scripted L for the line. It's not really a point or position vector the way other forms are. So this is an awkward form to use to find points on lines, but this at least demonstrates what this parameter means. Generally speaking, I wouldn't use parametric form to find points on a line unless I had to. Okay, we'll keep going. Determine L2. Oh, determine if L2, which is given there, is parallel, perpendicular, or neither to L1. And again, this is just getting us thinking about these things, and this is getting us used to working with equations of lines written in these different notations and how we can get properties of these lines, and all of this stuff is going to just, the better we are at all these little things, the better off we're going to be, okay? So what tells us that two lines are parallel, perpendicular, or neither? In grade 9, it would be the slope, but we're not talking about slope anymore. So what is it that we're talking about? We're talking about the direction vector. That's kind of like the slope of the line. So if I want to see if two lines are parallel, perpendicular, I have to compare their direction vectors. So D1, direction vector 1, I'm just pulling this straight from here, 3, 5, and remember, I turn that into the direction vector there. So yes, writing the vector form of an equation is useful, but what if I didn't have to write the vector form? I was given parametric form, and I just had to write the direction vector because I had to do this question C. Well, that's the same as similar to coming up with the equation of the line, just coming up with the direction vector, right? So that's something that I need to know how to do. And D2 is -5, 3. Now, what is going to be true if the vectors are parallel, what is going to be true if the vectors are perpendicular, and if neither of those things are true, then neither, right? Well, if they are parallel, what does that mean? From the last unit, think about this. We talked about vectors being parallel, perpendicular, or neither. Two vectors are parallel. There's two ways we can look at this. Two vectors are parallel if and only if their cross product is equal to 0, right? That's one of the ways. Now, a little note here, reminder, there is no cross product in two space. So since we're working in two space, that's not going to help us. So we can't take their cross product. Even if we could, that's probably the harder way. The other way that we think of vectors being parallel is if one is a scalar multiple of the other. So there is no k, and I'm just going to state this, there is no k such that d1 is equal to k times d2. And how do I know that? Just by inspection. I can't take a multiple of this and turn it into that, right? If I had 6, 10, well, that would be 2 times d1. That's what we mean, reminder, by a scalar multiple. But there is no such k. Therefore, these are not parallel, or we sometimes, again, call that collinear. Okay, so I've ruled that out, that they're parallel. That's what I would look for parallel. Yes, cross product can tell us that as well if we're working in three space, but probably just looking at scalar multiples is easy if you have both direction vectors. Now, what's the thing that tells us if two vectors are perpendicular to each other? And this will work in two space. The dot product. And this is why everything we did in the last unit is so important, because we need to know, and we need to know quickly and easily, what the cross product tells us, what the dot product tells us, what they're used for, how we use them, like what their actual formulas are. But remember, if the dot product is 0, then they are perpendicular. So d1 dot d2 dot product is 3 times -5 plus +5 times +3, which is -15 plus 15, which is 0. Therefore, L1 is perpendicular to L2. I don't say the direction vectors are perpendicular. It didn't ask me about that. It asked me whether the lines are parallel perpendicular. So this is a bit of a sticky point, but nevertheless, so the lines are perpendicular. Okay, so dot product is equal to 0. So the dot product, cross product are not going away. They're going to be big in this unit. And finally, write the equation of L1 in standard form. So we're not going to see a lot of standard form of equations of lines because we're more interested in the new notation now that we're getting into it. But remember, what is standard form? Ax plus by plus c equals 0. And we've done a lot of this in the calculus portion of this course. And for this, we need slope and a point. Okay. So the nice thing about this, how do I find the slope of a line? Well, I use my formula and I find it between 2 points, and I have 2 points. And then I need a point on the line and I have 2 points, so I can just pick one of those points. So I'm going to find the slope, which is y2 minus y1. And again, this is really grade 9 stuff, but you know, the beginning part of this unit is about being able to do all these different things and remembering all these little details of lines. So all these little questions that we do with lines will just help us tap into that knowledge. That's why we're doing this kind of thing. So this is 54 minus -1, which is +1, over 28 minus -5, which is +5, which is 55 over 33, or 5 over 3. Okay, and then we use y minus y1 equals m times x minus x1, just like we did in the calculus part at the point. Pick your point, doesn't matter, right? So I'll pick -5, -1, and where m equals 5, 3. So y plus 1 equals 5 over 3, x plus 5. Multiply by 3 on the other side, I get 3y plus 3 equals 5x plus 25. And moving everything to one side, I get 0 equals 5x minus 3y plus 22. And that is the equation of the line in standard form. Finding equations of lines and other things is a lot of what we're going to do. Thinking about properties of lines, whether they're parallel or perpendicular, whether points are on the lines, finding points on the lines. Some of this is going to be important for what we're doing next in this unit. Some of it is just about getting used to the notation, but you're going to notice that that's a lot of what we're doing over the next few days to get used to the properties and used to the notation is just, again, all these little kinds of questions that we can do. So your homework is the worksheet, just some of it, not all of it. And I believe we'll be using the same worksheet and other questions from it for some of our practice for tomorrow. But that's it for today. So we saw 2 of the new forms, like notations or forms of equations of lines that we're going to look at. And we saw vector form and we saw parametric form. And these are kind of the 2 big ones. So we need to know what their form is and then start to get an idea of how to understand the line from that form. Just like back in grade 9, when we had y equals mx plus b, and here you go, here's another reminder, y equals m, which might be 3 over 4, x minus 7. When I look at that equation, I know that the y-intercept is -7 and I know the slope is 3 over 4. So I could quickly sketch it. -7 and up 3 over 4, it's going to go like this, right? I could quickly sketch that line. That's the whole point of this stuff, is looking at the equation and knowing some properties about it. I mean, remember functions. That's what functions was all about, getting properties out of the equation. Well, again, that's what we want to do with parametric form and with vector form, is be able to quickly look at the specifics and start to pick out properties and then be able to do things with those properties of that particular line, right? So that's really what the first part of this unit is all about. And like I said, today was parametric and vector, getting used to equations of lines and some of the different things that we can do with lines.